Another key experiment is known as Compton scattering. Compton scattering is just like scattering visible light, as we see happening in the atmosphere, except we use much higher energy, much shorter wavelength, X-rays. So we begin with a beam of X-rays, and we have these collimating slits, which make sure the X-rays come in a narrow beam. The X-rays then hit this target and scatter around to all different directions. But we detect them at one particular direction, and we measure the wavelength at that direction where we've scattered them. Normally, light will come in, interact with electrons, bounce off, and go in all different directions with the same frequency that it came in with. Same frequency, same wavelength. However, it was discovered that if you hit electrons with very short wavelength, very high energy waves, this is about 70 nanometers, about 1/10 the wavelength, or 10 times the frequency and energy of visible light. If we hit electrons with that kind of light, then as we shift around to larger and larger angles, we see the scattered light coming off at longer and longer wavelengths, suggesting lower and lower energies. So the question is, why is it that if we hit electrons with light, very high energy light, the wavelength shifts depending on what angle we're looking at? There's really nothing in the wave description of light to explain this. Light comes in at a certain frequency, the electrons should move at that same frequency, the re-radiated light should be the same frequency and wavelength as the incoming light. But there is a model that works if we treat light as having momentum. Imagine, for example, that we have a 2D conservation of energy and momentum problem, as I have here. And let's suppose that this is a ping pong ball, and this is a tennis ball. Well, if the ping pong ball misses completely, then it'll just leave with the same energy it started with. If it hits directly and bounces backward, it'll give a large portion of its energy to the tennis ball. Not all of it by any means. The tennis ball is very big and the ping pong ball will bounce off almost perfectly. But it's given some momentum to the tennis ball, which means it has to take some energy with it. Going between these two extremes of missing the tennis ball completely and hitting and bouncing backwards, we have the possibility that the ping pong ball deflects off to the side. The further the ping pong ball deflects, the more energy, the more momentum it gives to the tennis ball. As a result, the more energy the tennis ball picks up, and the more energy the ping pong ball has to lose. That's exactly what we are seeing here. When the light goes straight through, that's just like the ping pong ball missing the tennis ball. As the light glances off to larger and larger angles, it becomes longer and longer wavelength, suggesting that it has less and less energy. Lower frequency, less energy. So we can explain this if we give light some sense of momentum as well as a sense of energy. How much momentum do we give it? Well, it turns out the rule is fairly simple. We know from our chapter on relativity that E squared is equal to P squared C squared plus M squared C to the fourth. If we assume photons have no mass, this term is 0, and the energy is simply equal to the momentum times the speed of light. So the momentum will just be the energy divided by the speed of light. That's Planck's constant times the frequency divided by the speed of light, but frequency over the speed of light is nothing more than 1 over the wavelength. So we say the momentum of a light wave is Planck's constant divided by the wavelength.